and get the slideshow from current slide.
Even though there's not that many people in here.
Yeah. Okay. Actually, yesterday morning in my first class, I was fiddling around with saving because I hadn't been able to save the Thursday evening class from the last week because we left early Friday morning, and you know, then we were at the farm. The DSL was so terribly slow I didn't even try, and so I was going to have it uploading while I was teaching my first class. I did all that stuff and then started teaching and forgot to start this.
Yeah, you told me.
Oh, I see. Okay. All right. Anyway, let's get going here. We're example 3, top of page 191, finding a basis for a subspace. Find a basis for the subspace of R3. So let me get my pen black again. Okay. Yeah. Find the basis for the subspace of R3.
Don't forget to do.
Right. Spanned by, okay, this set. This is your spanning set. V1, V2, V3. Okay.
Giving my V's wings because
What's that?
I've started giving my V's wings.
Yeah.
Because I can't sometimes tell my V's from my U's.
Oh, okay. Sometimes my V's and R's look too much alike.
Oh yeah, because
I separate. Yeah. So, especially if velocities and position are in the same problem, have to be really careful on those. Okay. That's equal to the set made up of -1 to 5. Probably we've had this before, but I don't recall. Good. Maybe not. I don't recognize 303. Yeah. And 518. Okay. So find the basis for the subspace spanned by this. Well, a basis has to span the set, so we know that we've got the set that spans it, but we don't know if they're linearly independent.
Right.
So what do we have to do to see if they're linearly independent?
Put it in the matrix.
What's that?
Put it in the matrix.
Okay, how would that look?
Are they in columns?
Yeah.
Like -1 to 5?
Yeah. 3, 0, 3, and 5, 1, 8. Now, how that comes about, you do a C1 times that one, C2 times that one, C3 times that one, and then you want that to equal the 0 vector, and you want to see if that's linearly independent or dependent. You know, so when you do that, that sets it up this way. So yeah, that's exactly what's happened here.
You're going to do 3 steps at once here.
What's that?
Do 3 steps at once here.
Okay.
Right, so we're going to do 2R1 times R2, or plus, R2.
2R1, whoops, writing it in the wrong place.
Or plus R2. Then 5R1 plus R3.
2R1 plus R2 goes here, and 5R1 plus R3 goes here, and then you're going to change the negate R1. Okay.
Alright, so we end up with a 1, -3, -5. You go ahead and write this down. 0, 6, or no, yeah,
6.
and then 11.
Yeah.
And we get a 0, 18, and 33.
Mm-hmm.
Huh. Well, that's okay. If you multiply the middle row by 3 and then add it to the last row, you get a row of zeros.
Yeah, -3, but yeah, got it. Right. So this is not, the third is not linearly independent. The first two are. So the third can be a linear combination of the other two. So the basis, let's call it B, for this subspace spanned by that would be just the first two, V1 and V2. Because V3 is a linear combination of the other three. So that could be, now, it's not the only basis, but it is a basis. -1, 2, 5, and 3, 0, 3. Wrote funny, but it's okay. All right.
He goes on talking about some
yeah. Now, okay.
There's the end of the example.
Yeah, they wrote it differently. They did the transpose of this one. They lined them up according to rows. Okay. Then they did it and found out that and basically what they were doing was finding that the two what we were doing was showing that the C's, the last C didn't have to be 0, so that basis would work. But they said that the first vector, which is exactly what the first vector was before, and the second one, which was 0, 1, 3, they form a basis. But guess what?
Actually, the first one is the negated version of the first vector.
I'm sorry, yeah. Actually, according to that, this is rather strange too. 1, 0, 0 and 1, -2, -3 would also be a thing. And you could get that with noticing that if you went back to do these two, then just divide everything here by a -3 and you get a 1. So there's a lot of different vectors, but those two would be a basis as well. They're not independent. They are independent of each other. Now, and what they did, the difference in what we were doing, we were setting C1, C2, and C3 and setting it equal to the 0 vector, and found out that not all the C's had to be 0, so the third was a linear combination of the first two, so done. Okay, but what they were doing was lining them up in rows and showing that the third one was a linear combination of the first two, which is exactly what we showed too. So I just went back and said those two, they had the first one being exactly like it was, and they just rearranged that one, but it's still linearly independent with both of those two. So theirs is probably a little bit neater way of doing it, so fine. Okay.
I mean, they're both true.
Yeah, both true. Now, to find the basis for a column space of a matrix A, you have two options. On the one hand, you could use the fact that the column space of A is equal to the row space of A transpose, true, and apply the technique that we just used, okay, to the transpose. On the other hand, observe that although the row operations can change the column space of a matrix, they do not change the dependency relationship among the columns, and you're asked to prove this in exercise 75, should you choose to do that. For example, consider the row equivalent matrices A and B from example 2. There it is, one that we had last time. Okay. Notice their row vectors are A1, A2, A3, and A4, and the B is B1, B2, and then B3 and B4. Okay, but because you have two rows at the bottom of all zeros, you can only okay, it just says, notice that columns 1, 2, and 3 of matrix B satisfy that B3 is equal to minus 2B1 plus B2. Do I buy that? Oh, B3, yeah, okay, yeah, that looks true. Minus 2, and the corresponding columns of matrix A satisfy that A3 is minus 2A1 plus B2. A2, I'm sorry. Similarly, the column vectors B1, B2, and B4 of the matrix B are linearly independent, as are the corresponding matrices of matrix A. Now, I'm trying to rationalize what they're saying here. Yeah. Is there any way to look at that and know that that could happen without? Well, here's the thing: if in row echelon form, if you have a leading one in any column, that column is linearly independent from the others. Okay, so that's why B1, B2, and B4 are linearly independent, because you see they have leading ones. B3 doesn't have a leading one anywhere in it, so therefore it can be written as one of the others. So you might say, do they have to be leading ones? No, but you'd have to be able to get them there by just dividing by whatever that leading thing was. It wasn't 0. So, while what they said is true, I think that would be the better statement to derive from this. Not, can you figure out a way to make them linear combinations? Well, yeah, you can. Well, why don't you just look at the leading ones? I don't know. I just sort of am lazy and like to shoot right for the, what part makes sense here? That makes sense. Next two examples show how to find the basis for a column space of a matrix using that method. Okay, so what we'll do is clean the screen here and do example 4. Find a basis for the column space of matrix A from example 2 that's not matrix A from it. Oh, they did a transpose. That's right. Okay, I was going to say. Okay. So, find the basis for the, see, this is just giving me, example 2 says find the basis for the row space, and now they're finding basis for the common space. And I think column space, I thought, that's not the same problem as example 2. It's a different problem, but using the same matrix. Okay, so doing it their first way, which was then to write the columns as rows, otherwise write the transpose, that gives you 1, 0, -3, 3, 2. 31040, 1162 negative 116 negative 2 negative 4, and 301 negative 1 1 negative 2. Okay, it's to find the basis for the column space. Write the columns as rows, which is the transpose, and then do your row reduction. And that would be right. Right. 4. Okay. 1 0 negative 3 3 2 stays the same. This becomes a 0, a 1, 9, negative 5, negative 6, right? Okay. That would be a 0. I'm trying to read my writing there. Yeah, that looks like a 1. 9. Isn't that just a, yeah, negative 5. And negative 6. Yes. 0. Yeah, 8. Yep. 8, isn't it? Okay. Yeah, nothing wrong with that yet. Except that row 3 disappears, so I would move it to the bottom. Okay. So your basis, let's say, find the basis for the column space. Here's what it would be, 1 0 negative 3 3 2, and you can leave it as 0 1 9 minus 5 minus 6, and what would be your last one?
0 0 1 negative 1 negative 1.
Got it. You could have the bigger thing, but why? That would be the basis for that. And what did they come up with? It looks like the same thing. 1 0 negative 3 3 2. They write them transpose. Okay, I don't care. Okay, I wrote them as vectors. Okay, 0 1 9 negative 5 negative 6, and 0 0 1 negative 1 negative 1. Got it.
That's it.
Yeah. Example 5.
Column, the form of that's the basis of column space.
What's that?
That's a basis for the column space.
Right. And of course, the vector space that came from was R5, but this is a basis for the column space of this would just be three-dimensional. The vectors all have 5 components, but just 3 of those make the basis for that column space. All right. Now, example 5, finding a basis for the column space of a matrix. Find the basis for the column space of matrix A from example 2 by using the dependency relationship among the columns. Okay, so I think they say go to matrix A, do the row reduction which we have in B, and then which ones are independent, and you go back to columns, and then you would have the 1 0 0 0 0, 3 1 0 0 0, and 3 0 1 0 0. That would be what I would write down but they're writing the original ones that correspond to those. 1, 0, negative 3, 3, 2, 3, 1, 0, 4, 0, and 3, 0, negative 1, 1, negative 2. Yeah. So they just went back to their original, which is fine, you know. And you just got that by doing the row reduction and then picking those that had leading ones or leading non-zeros. Okay, whatever.
So, what happened here?
Okay.
You just took, right, so you looked at the...
So they said you can do it two ways.
Right.
Write them as that one. This is method 2. What they did with that was just use this as a, you know, as it sat, and then look at the ones that are independent, those leading non-zero leaders.
And then they entered them in.
And then they went back to those. So it was the first, second,
and maybe like fourth. Yeah.
but they wrote them as that. So,
And that's all there was to it.
yeah,
That's all there was.
yeah,
I guess since we already had it, that was easy.
yeah, exactly.
But if we didn't already have it,
We'd have
get
to
it
do
in
all
row
that.
echelon
Exactly.
and then rewrite the 3 rows.
Exactly. It says, notice that the row echelon form B indicates which columns of A form the basis for the column space. You do not use the column vectors of B to form the basis. Why not? I mean, it would be perfectly fine to, but yeah, you can go back to, it just indicates the column, okay? But those others would work too, I think.
What's the difference between a column space and a row space?
It's just which you're dealing with. I mean,
Whatever they're asking.
if it's a 4 by 5 matrix, then the column space would be the 5 4-dimensional vectors, and the row space would be the 4 5-dimensional vectors. So they're different spaces completely, yeah. And it just depends on which one you're doing. Yeah, yeah. Now notice that the basis for the column space, in example 5 that we just did, is different from that obtained in example 4. In example 4, they used the top 3, you know, when they did the transpose, but that, and this is why I said, what difference does it make? Well, their W1 was their first column, their W2 was the 0, 1, 9 negative, you know, and their W3 was, because they had flipped them, you can't take the third column here, you have to keep up with what you did. That row of zeros came from the that third one, and you move that to the bottom. So you do have to watch for that, okay? That is the only thing I would warn about that. Notice it different from that. Verify that these bases both span, yeah. Also notice that in examples 2, 4, and 5, that both the row space and column space of A have dimension of 3. There are 3 vectors in both bases. The next theorem generalizes this, and that's what this theorem is. And since I think it's Victor that doesn't have a book, and maybe Norman has a different book. Let me do this. If A is an M by M matrix, okay, then the row space and column space, okay, of A have the same dimension. Okay. Now let's go back and turn back in time, okay, you're finding the basis of rows of the row space of this 5 by 4 matrix, okay? When you did row reduction, you got 3 rows with 2 zeros at the bottom, 3 rows without all zeros, and 2 at the bottom. So it's a basis of 3 vectors. Okay.
So as long as the number of rows is different from the number of columns, they'll have the same dimension.
Yeah.
But if it's a square matrix, something different would have to be possible.
No. No. Okay. Whichever. However, rows or columns, what makes that a example 2 be there? The basis, the last 2 rows are all zeros, so the top 3 are linearly independent and they span the set that you're dealing with. So notice you have 3 leading 1s, or 3 leading non-zeros anyway, okay? But then when you flip them around and do it the other way, either in example 4, which you did the transpose, you still have 3 leading 1s. And because when you do the row reduction of these, whichever you did, the transpose or not the transpose, you're going to wind up with those 3. I can't say it's the same ones because they flipped them and moved 0 rows and stuff like that. Same number of them. And then you do it the way they did. Well, no, they didn't do it again.
I was just wondering, the theorem says if it is an m by n matrix, then the spaces are the same. But what if it's an n by n?
Okay. Again, it'll be because you'll still, when you row reduce a square matrix, you'll have a number of leading non-zeros, and that's turn it around and still that number of leading non-zeros. Okay.
Basically any matrix.
Yeah.
So,
yeah. Any n by n by m, whether n or m are the same or not the same.
okay.
Yeah. And what I was looking for was the okay. After example 3, but before they did example 4, they took that same A that they had before and then looked at the column. Okay. Let's start again. Example 2 was looking at the basis for the row space. Okay. And the row space were 4-dimensional vectors, okay? But you wound up with 3 of them because the last 2 rows were not linear. But you had three rows that started with non-zero entries, okay? Well, then they were looking at the column space of those same, and those were 5-dimensional vectors, but you only had 4 columns then. And when you did the row reduction, you're looking at the same vectors that have, even though they're no longer the leading, because now you're looking at the columns rather than the rows, you count those that have those leading non-zeros. They happen to all be 1s here. And so you have 3 independent ones. That third one, because it has a 0 right next to the other one, those are linearly dependent on, you don't have that extra entry there. Okay, so therefore it works the same way. Or if you transpose them like they did in example 4, you still come up with the same because you wind up with 3 leading non-zero entries. They don't say that word, but that's how I think of it. So yeah.
Alright, either
Yeah.
one work?
That what?
So number 3, could you use either column or row space since
Yeah.
they just wanted a basis for the subspace?
Right, exactly. But then you have to remember which it is that you're doing. The basis either was the top two, the first two of those are the reduced first two of those. But don't transpose and then make the column space the rows,
Keep your vectors
yeah,
in line.
keep your vectors in the same line. So you are talking about the same things. But I was talking about the ones below example 3, but above example 4. Yeah, it works out the same. Here's their little proof here.
Little?
Yeah. They have
That's
M vectors,
fast.
okay, M row vectors, and N column vectors. So it's obviously an M by N matrix because you have M row vectors, N column vectors. And it doesn't matter whether they're the same or different. Which one's bigger or smaller, it doesn't matter. So there's your matrix made up of those. Suppose that the row space of A has a dimension R, the row space, and a basis of, and then they introduce some new vectors, B1 through BR. Okay, R has to be, of course, less than or equal to M, okay, because you can't have more than you had to begin with. Okay. Using that basis, you can now write, sorry, I can hardly talk. You can now write the row vectors of A as vector 1 is some linear combination of those R vectors of B, and every one of them can be written as a linear combination. Rewrite that system of vectors. Yuck. Yeah, I really want to do this. Yeah, I believe so. What you're doing,
What it looks like to me is it's going to get really bogged down and more, it'll confuse the issue.
yeah, yeah,
So, definition
yeah.
of matrix.
That is a nice little.
And
But
I
anyway,
was,
yeah.
while you were going back through and talking about the examples and stuff, I was kind of looking at it as just
Yeah. Now let's pick up then.
definition of the rank matrix.
Dimension of a row or column space of a matrix is also called the rank of the matrix. So we were calling it dimension, now we're going to call it rank. Some texts distinguish between row rank and column rank of a matrix, but because these ranks are equal, this text will not distinguish between them. Why would you? Okay. So here's the definition of rank of a matrix. The dimension of the row or column space of a matrix A is also called the rank of A and is noted by rank of A. Okay, nice. So my question is, why change the name? It was all right to call it the dimension. Why are now you calling it rank? Well, maybe we'll see later. So let's do example 6. To find the rank of matrix A, shown below, convert to row echelon form to get B. So here's A. 1 minus 2, 0, 1. 2, 1. 5, negative 3. 0, 1, 3, 5. Now, how do you get the rank of that matrix? Row reduct, yeah. Negative 2, row 1 plus row 2. Okay. And we leave that one alone for now. 1, negative 2, 0, 1, 0, 5, 5, negative 5. And 0, 1, 3, 5. Okay.
We can probably reduce that to ones.
Yeah. 1, 1, negative 1. Okay? What now? I'll go on to make it easier to read. Wipe out the 5 parts. Ooh, I wiped out too much. That was a positive 1, wasn't it? Yeah. Okay. Next. Right. Keeping the first row, 1, negative 2, 0, 1, 0, 1, 1, negative 1, and 0, 0, 2, and what? 6. Okay, I couldn't hear what you said.
Then we can divide the bottom row by 2, and we have row.
Yeah, yeah. But if all you want is the rank, what is the rank? 3, exactly. What would be the... What's that?
Because we have 3 leading non-zero.
Yeah, that's how I say it, and then I don't have to change that to 1. Okay, but it's easy to do. Yeah. So, yeah, rank 3 for whether you did column or row, rank is 3. Because they're linearly independent from each other. Now, this is maybe a little bit of why we shifted to rank. I'm not sure it completely justifies it, but a little bit. Row and column spaces and rank have some important applications to systems of linear equations. Consider first the homogeneous linear system AX is equal to 0. Exactly. All right. Where A is an M by M matrix. M rows, N columns. X then, of course, would have to be, if it has, A has M rows, N columns, wait, let me say this right, then X would have to have N rows. So that would be some vector x1, x2, x3, dot, 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 down to x sub n. Okay? Now, I wrote it as a column vector. They wrote it as a row vector, but then did the transpose of it. Fine. It just has those entries. That's a column vector of unknowns. And what about the 0 vector? What would that have to be? That would be the 0 vector, 0, 0, 0, dot, dot, dot. Yeah, the last one would be a 0. How many of them you got?
M.
That would have to be M, exactly. That would have to be M by 1, okay? The 0 vector of Rm, true. The next theorem tells you that the set of all solutions of this homogeneous system is a subspace of Rn. Okay, a little bit on the side here. All right, no, we haven't gotten to the term yet, so we won't get to the side. So here's the theorem. I'm going to write it down. I'll take up all the slide I need. If A is an M by M matrix, M rows, N columns, then the set of all solutions of the, include that. All solutions of the homogeneous system of linear equations, so of all solutions of the homogeneous system of linear equations okay, AX equals 0. Okay. Where, sorry, set of all solutions of the homogeneous system of linear equation AX equals 0, where A, of course, is m by n, x is n by 1, and the 0 vector is an m by 1. Okay? This is a subspace okay, of Rn. Okay. The set of all solutions, yeah. Its x vector is in n space because it's a 1 by n, n by 1. This is a subset. I've written that already. And just, wait a minute. Then the set of all solutions of this is called the null space. Okay, the null space of A. Okay, and is denoted by n of A. Okay, null space of A. So the null space of A is equal to the set of all x's, vector x's, in Rn, such that AX is equal to 0. Okay? The dimension of the null space of A is called the nullity. I think I got too many syllables. Nullity. Nullity. Nullity of A. It sounds better, but it's nullity. It just doesn't seem like it has enough things. Liddy? I don't know how you say it. Okay. Frankly, I think this is the only book that I've taught from. Certainly when I took linear algebra, we talked about null space. I don't remember talking about the nullity because the null space defines it perfectly fine. The dimension of the null space is the dimension of the null space. Why give it another name? Okay. So, let's see if we can make some sense out of this.
So basically, wherever this is where A equals 0. Sort of.
Where what?
Where AX equals 0. So it's just where in Rn does the matrix and another vector equals 0.
Okay.
Strange.
A is an m by n matrix. It's the set of all solutions of the homogeneous system of linear equations AX equals 0. It's a subspace of Rn because it has n entries in it. And it's called the null space of A, and is determined by, I'm pretty sure that's what it said, but
It's denoted
denoted by that thing.
by
N of A. Okay. Now, sorry.
and it's
If the only solution of A of that equation was the trivial solution, which of course is a solution. There's always at least one.
basically that's what the x vector would be, just 0.
Yeah,
It'd be multiplying it by the 0 vector to get the 0 vector.
right, exactly. Okay. Then the nullity null space, the dimension of the null space would be.
But if
one.
you can use
But if
more
there are
than
some
one,
others, yeah, right.
it would be however many others there are.
Yeah, the one plus how many others, yeah.
So it'd be, if there were the trivial solution and two others,
Yeah.
then it'd be 3.
Okay, let's see imagine what those others would look like. Remember, if you did the row reductions and you came out with things and you had, say, 2, 3, 5 columns that had leading non-zero entry cell, then you let those be, remember, S or T or something else, and you could work from those, and the others would be so you might have one and zeros, something there, but then you might have others with something of ST or whatever. Well, the zero factor would be when all the others if it was a square matrix and you had ones down the diagonal, okay, no others, that would give you only the triple solution.
Right.
If you had anything else that had columns without leading non-zero, then those would be
additional solutions.
yeah, that would be your nullity. Now, you don't have to add one to it because what I was trying to say is, let's just say you had a R, S, and T, 3 of them that had those in them. Well, then X1 would be some linear combination of, maybe X2, some of the others, and those. And if all those were set equal to 0, that would make everything else 0 too. So it would already be included in it. Okay. But if it came out just with that, then you would have 1. So that's the dimension of the null space. That was poorly said, but say again.
It's a neat little thing at the bottom.
Yeah. About the barcodes? Yeah. And that could be a paper topic if you're interested enough to do that. But the proof here that's listed, if A is an M by N matrix, you know that X has size N by 1, and the set of all the solutions would be a subset of Rn. All solutions. That set is clearly non-empty because the zero vector, the trivial solution, works always. Okay, you can verify it's a subspace by showing that it is closed under the operations. Let's see. Is that what we're trying to prove here? Is that then the set of? Oh, okay. Skipped right over that. That's the first part of it. That this set of all solutions for that homogeneous thing is a subspace of Rn. Certainly that's got to be true. And then the second part is just that how you define that. Right. And okay, you can verify that it's a subspace. Got that. Let x1, x2 be solutions of vector blah blah blah. C is a scalar because ax1 equals 0, ax2 equals 0. You know that a of x1 plus x2 equal to 0. So, goodness gracious. Oh yeah, they're just showing that addition is defined in scalar multiplication. And then, like you said, at the bottom of the page, the linear algebra applied. Postal Service uses barcodes to represent such information as zip codes, delivery addresses, that kind of stuff. The zip +4 barcode shown on the left, 13215-5523, showing, well, it starts with a long bar because that's a 1. The zeros are the short bars. A series of short and long bars representing each digit in the zip plus 4 code and an additional digit for error checking, and ends with a long bar. Okay. The following is a code for the digits. That's totally bizarre in my mind. Why wouldn't 0 be all little bars? And 1, that makes sense.
But, I mean, it's a computer reading it, though.
What's that?
I mean, it's going to be a computer reading it.
Right, exactly.
It's just however they program it.
I know, but
You would think
why wouldn't they program it that way? See, the 1 makes perfect sense. 0, 0, 0, 1 with his check of 1. Because that last bar is your check.
And then 2
Okay.
has a space.
2 is 0, 0, 1, 0, which is 2 in binary.
Right.
And it has a checksum of 1. 0, 0, yeah. See, all the others are exactly what I would expect them to be, except 0. Why would it be a 1, 1, 0, 0? That's not a 0. That's, I don't know.
Let's see. You go to 1, 1 at the end, and then 1 space. You get 1, 1 space. Well, why does it go from 3 to 4 having a long bar at the end and then not?
Okay, well, the long bar at the end is the checksum of the others. You have 0, 1, 0, 0. Add those together, you get a 1. So that's why there's a long bar at the end.
Okay, so
Any that have 2 in it, the last one is
if it's odd, it had
1, and even
But
number is
we
the
have-
last digit is a
right.
0. Right. So all the ones make sense except 0. I don't know.
Well, if you look at it, look at how. All right, so 7, 8, 9, and then if you were to go to 10, it's 0.
Yeah, that's what I was going to say. That would be 10.
It's a base. It's
Yeah.
a base 9 thing. Though.
Yeah, I guess
It's
so.
not. It's not really. It's not binary. It's
Right.
a base 9. But I see what you're saying.
Yeah. All right. Never mind.
Nines are in everything.
Yeah. Yes. All right. So let's do example 7. We got time, right?
We got about 9 minutes.
Okay. Yeah. We can do example 7. I'm convinced. Watch me be unconvinced, but let's see it. Find the null space of this matrix A. 1, 2, negative 2, 1. 3, 6, negative 5, 4. And 1, 2, 0, 3. Okay. Now we jump from talking about
I already see one column's a multiple of the other.
is, yeah,
That's
column-wise, right. What you would typically do is row reduction, right? And you see you got a column problem there, but it's going to show up. It'll come through like that. Okay, so do a row reduction, and what would that produce? Negative 3 row 1 plus row 2, and negative row 1 plus row 3. So 1, 2, minus 2, 1, 0. No? Wait. Oh, negative. I missed my negative. That's all part of the equal sign. Never mind. Okay, yeah, that would be a 0. Of course, it would have to be. And that would be 1, right. And 1. Yeah. And the bottom one is a 0, a 0, a 2, and a 2 again.
And there's our issue.
Yeah. So this one's going to go to 0, 2. Okay? So what's the nullity? 2.
Yeah, that's 2.
Yeah.
Because
No, wait. Find the null space. I'm sorry, not the nullity. The nullity was 2, but find the null space.
okay, now let me ask you. The nullity is 2 because the bottom row is zeros, and then you have the 0 vector, right?
Okay. Let's hold off nullity for a minute. Okay.
Okay.
Yeah.
We'll come
Okay.
back.
Yeah. We'll come back. What is the null space? Okay. It's the set of all the solutions of the homogeneous. Okay. Then the set of all solutions of the homogeneous system equation is a subspace of Rn called the null space of that. So
My question is, they switched their top and then bottom row and ended up with the same thing, but just with the bottom row on top instead. You see that?
interesting.
I don't think it will.
Why did they do it? I'm not sure, but
Well, I guess if you were to switch those 2 rows, it might give you the same.
let's see what they say here. Solve the system, write the augmented matrix, and this is what they're doing. They're taking the A, multiplying it by an X. Why did I put the bracket there? I don't know. No reason to. And set that equal to the 0 vector. Doing this full out here. Okay. Okay. Because the system of equations is homogeneous, the right-hand column of the augmented matrix consists entirely of zeros. Yeah. And will not change as you perform row operations. So it is sufficient to find the reduced row echelon form of A. Why in the world did they do that? I don't know, but they did. That's fine. So let's go on and do ours too, just like they did. Okay. Choose x2 and x4 as free variables because you don't have a leading non-zero entry in those 2 columns. Okay. So let's see what ours turns out to be. If we let this be S and this T, is that what they did? I think it is. Okay. So x1 is equal to 2 minus 2s minus t. They did it slightly differently. Oh, you know what they did? Yeah, got it. Wait. They did reduce row echelon form. Okay. Not just stop at row echelon form. Do reduce row echelon form, and what would you do? You would do 2 row 2 plus row 1 is the new row 1 to get that a 0 above it. Let's see what happens with that. 0, 0, 1, 1, 0, 0, 0, 0. This would be 1, 2, 0, 3. So no, they didn't switch the rows, they just did one more step of row. They did reduce row echelon, which was equivalent to doing that. In other words, if you had switched, you would have saved yourself one step. But it's got to come up the same, and it did. In reduced row echelon form, it's got to come up the same.
Kind of interesting how it came back to the bottom row, though.
Yeah, it is. And almost essential for it, too, because the leading ones have to have 0 above and below, and you have a leading row there, and that row has a 0 below it. So anyway. So what does this tell us? That they call this x1, x2, x3, x4, x2 equal s, and s4 equal t, because they don't have that. So x1 is equal to minus 2s minus 3t.
But we don't have to account for the x1. Oh wait, okay, x1 equals. I got it.
Yeah.
I got you.
Okay, and x3 is equal to minus t. Okay. Now, here's what I was trying to say before.
x3 equals negative t.
Right. X4 was t, so this thing is equal to 0. X3 plus x4 is equal to 0, so that means x4 plus t is equal to 0. So, x3 plus t is equal to 0.
So, okay.
X is equal to 10. Okay. Now, here's what I was trying to talk about before. When you set these up and do them this way, especially when you have a reduced row echelon form, so you have zeros above and below all the leading ones, here there's just 2 of them, then if you let s equal 0 and t is equal 0, that means x2 is 0 and x4 is 0, then x1 is 0 and x3 is 0, because, so your trivial case is included, always, okay? Even if this had been a 4x4 and you had diagonal ones and everything else zeros, you had the identity matrix, then all 4 of them would be zeros. That would be included there too.
Okay, so the nullity only includes the 0 matrix when that's the only one.
Yeah, well, no, nullity of a, if it's the only one, then that nullity would be 1.
But if it's
Now we've got more than 1.
2
Okay.
plus the other one that's only 2. Nullity's 2.
Okay, well, let's see. We haven't gotten there yet. Okay. So, it said find the null space. Okay. Well, the null space, the basis for the null space is just these 2 vectors. Okay. Now, what are the 2 vectors? To make that everything a 0, certainly s equals 0, t is equals 0, that makes all 4 of them 0. Okay, we've said that one. But also, anytime that you would have let's see if I can, okay, these are your thing with x2 equal s and x4 equal t. Okay, that makes the full pattern here. Okay, so then you could write your x vector as, of course, x1, x2, x3, and x4. But if you wrote it using these, that gives you yeah. If this is your s, this is minus 2, 1, did I count that? Yeah, 0, 0, plus minus 3, 0, minus 1, 1. Yeah. It would be s here plus t there. Okay? I wrote it up there, but didn't really need to. So, any linear combination of these, pick an s, pick a t, and they're always going at the 0, okay? For that, set. So therefore, the basis for your 0 vectors would be these 2 vectors, this one and that one, because any common, pick any, that's like your C1 and your C2, okay? Any combination of those. So in other words, the 2 vectors are solutions of that, and all solutions of that is a homogeneous system or linear combinations of those 2 vectors. So now we get to the third part.
We are 3 minutes over.
Okay, let's wrap this up then. The number of columns, okay, in example 7, the matrix A has 4 columns, okay? So the number of columns is equal to the rank, which is the number of columns with leading non-zero entries, okay? That's 2. That's the rank of 2. Oops, rank of 2 plus the, say again, nullity of 2 and number of columns of 4. Yeah.
So, number of columns equals rank plus nullity.
And this is nullity, by the way, made up of 2 vectors,
Okay, so
in the basis.
they were just asking for what the null space was.
The null space is,
Well, no, you can take the number of columns and subtract the rank, and you get the nullity.
yeah. Right. Yeah, exactly. Okay. We'll start next time with Theorem 417, which I think talks about that very thing. So we'll begin there on that page. Homework exercises here. 1 or 3 or both, any of the odds 5 through 9, 11 or 13 or both, 15 or 17 or both, any of the odds 19 to 23, and any of the odds 25 through 35. And I think any of the odds 37 through 45. Let's see. Is that going into what we said? Maybe leave those off until we do the last. Okay. We'll go from there. Now we'll end it.